Hello, in today's video we're going to be talking about this last quantum number of our set of 4, which is the spin quantum number, and then we'll also be talking about the Pauli exclusion principle, which relates this spin to our last quantum number. So we have 3 quantum numbers already, 3 that we've learned throughout the last week. We have the principal quantum number, we have the angular momentum quantum number, and we have the magnetic quantum number. These 3 identify the orbital that we're in. Orbital. The last quantum number, which is the spin quantum number, that is designated with an m sub s, actually tells you which electron you're dealing with. And it's given only 2 different values. Each electron, an electron can only have a possibility of 2 different values. Now, we can either assign an electron a positive 1/2, or we can assign an electron a negative 1/2. These are the possible values that we can give to an electron. Now, it really doesn't matter which one we give. However, the Pauli exclusion principle, which we will talk about, discusses how many of these can go in each orbital. So let's look at this. Let's look at this positive and minus 1/2. What does this really look like? How can we think about this? If we think about an electron, and this is the axis on an electron, and we have a second electron here, axis on that electron, the plus 1/2 would be going clockwise, spinning around clockwise. The negative 1/2 would be spinning around counterclockwise. So really what's the only difference between these 2 electrons, they weigh the same, they have the exact same charge, it's really hard to distinguish between these 2. The only way we can do that is to see, well, really one looks like, or we can think of it as spinning around clockwise, positive 1/2, and the other one we can think about as spinning around counterclockwise, or negative 1/2. So this is our last quantum number. We know all the different values that n, l, and m sub l can take. Now, for the m sub s, depending on how many electrons we have, it can either take a plus 1/2 or a minus 1/2. So let's see how we can, an example of this. So counterclockwise, clockwise, counterclockwise. So let's take n equaling 1. If n equals 1, we know that the possible L values are going to be 0, because L ranges from 0 to positive, 0 to n minus 1 in steps of positive 1. M sub L, which is 0, it can only range from minus L to positive L, so that's going to be a 0. And if we're talking about electron number 1, we're going to have an m sub s of a plus 1/2. Now, if we're looking in the same orbital, for electron 2, let's say that the second electron is in this exact same orbital as the first electron, we're going to have n equaling 1, l equaling 0, and m sub l equaling 0. But the Pauli exclusion principle states that no 2 electrons can have the same set of 4 quantum numbers. Already, these 2 electrons have the exact same orbital. 3 of their quantum numbers are the same, so by the Pauli exclusion principle, the second electron has to have an opposite charge, an opposite spin. M sub s is going to be the minus 1/2. So this is the only difference between these 2 electrons. They're in the same orbital. They're, one is spinning clockwise and one is spinning counterclockwise. And this is using the spin quantum number as well as the Pauli exclusion principle to identify which electron we're talking about. Now, if we were to look at this, we can see, we'll do the Bohr model just because it's easier to draw. We have electron 1 here. We have electron 2 here. From these quantum numbers, they're both in the 1s orbital. This electron is going to be spinning clockwise. This electron is going to be spinning counterclockwise. And that's the only difference. Now, another thing that the Pauli exclusion principle states is that each orbital can only contain 2 electrons. Well, that changes a lot of things. Now we know that any of our 3 quantum numbers that describe the orbital There can only be 2 electrons in each of those orbitals. So let's do another quick example. Let's do an example and count how many total electrons are possible to be fit into the n equals 2 principal quantum number. How many total electrons can we fit in there? We know that L has 2 possible values, 0 and 1. We know that M sub L of 0 equals 0, and M sub L of 1 equals -1, 0, and +1. Now, this would have 4 total orbitals that are allowed for these quantum numbers, for the principal quantum number of 2, and now we can count how many total electrons we can fill into that. There could be 2 here, a +1/2 and a -1/2. This one, we could have a +1/2 and a -1/2, +1/2, -1/2, +1/2, -1/2. So total, for the principal quantum number of n equals 2, we can fit in 8 total electrons in 4 different orbitals. So that's what we're going to be dealing with in the next video, is talking about the electron configuration. Now I do want to go through one more type of definition. We're going to be dealing with this a lot on Friday. So we know that each of these orbitals can contain 2 electrons. We now are going to start talking about differences in these types of electrons. So let's say we have our 1s orbital. I'm going to do the same thing I did in class where I shaded in. This is our 1s orbital, and this is our 2s orbital. Okay. You've seen me draw this in class before. 1s, 2s. Now we're going to have a difference. This bigger shell, if all of these are filled with electrons, so we have the 1s has 2 electrons, the 2s has 2 electrons. Now there is a difference in those types of electrons. The electrons in the smaller principal quantum number shell are known as our inner electrons, also called our core electrons. And those that are on the absolute outside, the last ring out there, are going to be known as our outer electrons. Kind of makes sense. If the inners are the inners, this is going to be the outers. They're also known as the valence electrons. Valence electrons are where all the cool chemistry happens. They are involved in all of the bonding. The inner core electrons are generally not involved in the bonding of any compound, like a hydrogen bonding, or let's say a carbon bonding to a carbon. The inner core, those electrons are not involved in the bonding. Only the outer core are, the valence shells are. So we'll be talking about these valence shells on Monday and on Friday of this coming week. But I just wanted to let you know, we now have all 4 quantum numbers: principal quantum number, angular momentum quantum number, magnetic quantum number, and then our spin quantum number. This describes exactly which electron we're talking about in exactly which orbital. And now we also have, once we start increasing the number of shells, we have electrons known as the inner core, which are not involved in bonding, and we have electrons known as the outer electrons, or the valence electrons. And with that, I want to say we'll talk a lot about this tomorrow. We'll talk about what the interactions that play between these 2 types of electrons. We'll identify how many electrons are possible. We'll do a lot of different problems involving this material. So with that, I want to say have a great night. I will see you all in class on Friday.